Your next few labs are going to be about circuits. So here I'm going to briefly review circuits and talk about some of the laws that we have with them. So a circuit is just a combination of resistors and capacitors and other electronic devices connected by wires to something that provides a potential difference, a battery, for example. Within our circuit, we have current that flows. That current is our electrons, electricity that's flowing through the circuit, through all the elements. Current has units of amperes, which we represent as capital A. Resistance is the resistance to electrical flow. And our little devices that we're going to use called resistors are things that resist this electrical flow. So within a circuit, we represent our resistors as these sort of wiggly lines, these zigzags like this, okay? And so we can line up circuits in different ways. We can line up the resistors within our circuits in different ways. The two ways that we think about resistors in order to mathematically treat our circuit. Are our resistors in series or are they in parallel? So here I have an example of 3 resistors that are in series. When resistors are in series, that means that the electricity running through our circuit has to go through all of the resistors. That same current has to run through all of the resistors. There's no way you can divert any of that current. So these 3 resistors here are in series with each other. Now another way that you can align resistors in a circuit is in parallel. So here, when you are in parallel, we've got the current coming in here, and that current has to split in 3 different ways. It can split to go through this resistor or this one, and then it'll all combine on the other side of the resistor and exit out the other side. So here is an example of 3 resistors that are in parallel with each other. Our rules for resistors are different depending on whether our resistors are in parallel or in series. Now, we can always calculate Ohm's law for each individual resistor. Ohm's law says that our potential difference across each resistor is equal to the current through each resistor times its resistance. Now, when we have resistors in series, we can add up the sum of those resistors together to get a total or equivalent resistance. The total resistance for our resistors in series, you just add them up, okay? When we think about the potential difference across our resistors in a series, the potential difference sums together. So the total potential supplied by our battery in the circuit must equal the sum of the potential across resistor 1 plus the sum of the potential across resistor 2 plus the sum of the potential across resistor 3 and so on. The current is the same for any element of your circuit that is in series. Now, for our circuits that are in parallel, we can compute a total resistance for our resistors in parallel, but that total resistance is a little bit more complicated here. To find the total resistance of these 3 resistors in parallel, you have to take 1 over R total equals 1 over R1 plus 1 over R2 plus 1 over Rn and so on. Okay? For all of these resistors that are in parallel, the potential across each one of them is the same. Okay. If I took a little multimeter, which you'll be playing with in lab, across to measure the potential difference across each one of these resistors, it would be the same for all of these that are in parallel. But for all of these in series, that potential must add up to be the total potential that's coming out of our battery. And then because our current has to diverge in multiple ways, the total current through my resistors in parallel is equal to the current through resistor 1 plus the current through resistor 2 plus the current through resistor 3 and so on. Okay, so that is the idea that we're going to need to use for our next few labs that we're going to be working on, and we're going to use these rules for our circuits when we have resistors in series and parallel. We're going to be seeing the same thing in lecture 2. Here we are going to consider a circuit that has 3 resistors in series. So here's R1, R2, and R3. All right, so these are my resistors. Here is my battery supplying the potential difference. When I draw the battery in a circuit, I represent it as two parallel lines, but one of those lines is bigger than the other. The one that, the side of the battery that has the positive terminal is the longer side of the parallel lines. The part of my battery that has the negative terminal is the smaller parallel line. So this is different than what we use for the capacitors, for example, when both of the parallel lines are the same length. So our current is going to run through our circuit. It has to run through resistor 1, resistor 2, and resistor 3. Now what we are going to do is we've got our resistors in series here connected to a power source, and we are going to find the total resistance of the resistors in this circuit, and we're also going to find some other quantities here. And I've laid it out in a table. So here I have resistor 1, which is going to be 30 ohms. The unit that we use for resistance is a capital Greek letter omega, but it's the unit is spelled O-H-M, ohm. Okay. Resistor 2 has a resistance of 70 ohms. Resistor 3 has a resistance of 100 ohms. The larger the resistance, the more it resists the flow of electricity. Well, what we're going to do first is find the total resistance of our entire circuit, and then we're going to find the current through each resistors and the current through our total circuit, and then the voltage through our total circuit and the voltage across, or the potential difference across each resistor. Okay. So for your pre-lab, you might be asked a question where you only have to find the resistance of 3 resistors in a series, or the resistance of eventually 3 resistors in parallel. Then you can stop with the first part of the problem that we're working through. But some of the pre-labs, I'm going to ask you to go a little bit further, so you might as well watch this whole problem so you get the whole thing. Well, we're going to first find the total resistance of these resistors in our circuit. Now, when we have resistors in series, the total resistance adds up. So our total is just going to be the sum of R1 plus R2 plus R3. And so that's just going to be 30 ohms plus 70 ohms plus 100 ohms, and that gives us a total resistance of 200 ohms. And I'm going to write that over here, total resistance of 200 ohms. Right. Now with that, we are going to figure out what is the total current in our circuit using Ohm's law. We can go ahead and fill out our chart here. We know that our whole current is being supplied by a potential difference, or a voltage, of 10 volts from my 10-volt battery. Okay. So then I can use Ohm's law to figure out the total current inside my circuit. So V total is equal to I total, our current, times the total resistance. If I solve this for I, the total current in my circuit is the total voltage of my battery to the circuit divided by my total resistance. Okay? And so then my total current in this circuit is going to be 10 volts divided by 200 ohms, and that's going to give us a current of 0.05 amperes. The units on current are amperes. So for my total circuit, I have a current of 0.05 amperes. Now what's special about resistors in series is that the current is the same through every single one of them. So the current through each one of my resistors here in series is going to be the same as the total current of our circuit. So this is really easy. We've got 0.05 amperes of current running through each one of my resistors. Now to get the potential difference across each one of my circuits here, I can use Ohm's law. Right? So Ohm's law for each one of those resistors. And Ohm's law is equal to the current, so it says that the potential is equal to the current times the resistance. So you just compute this for each resistor. So the potential across resistor 1 is just going to be the total current, 0.05 amperes, which is also the same as the current running through that resistor, times its resistance, which is 30 ohms. And so that gives us a potential for my first resistor of 1.5 volts. 1.5 volts. You do then the same thing for each individual resistor in series to get the potential across it. So the potential across resistor 2 will equal the current through resistor 2 times its resistance, and then the potential across resistor 3 is going to be the current through resistor 3 times its resistance. So for V2, we get that the potential across it is 3.5 volts. For the third resistor, we get the potential across it is 5 volts. We have this rule that when our resistors are in series, the potential difference across all of them has to add to equal the total potential supplied by our battery. So if we come back here, if we added 1.5 volts plus 3.5 volts plus 5.0 volts, that's V1 plus V2 plus V3, we would get back 10 volts. So our circuit here does follow the rules that we have for resistors in series. If you're working on one of these pre-lab problems and all you have to do is find the total resistance of a collection of resistors in series, then you can just stop with this first part of the problem right here. But maybe I have a bunch of resistors in series and I'm asking you to find the potential difference across any one of these or the total current through the circuit. You would need to replicate different parts of the problem that we just went through here in order to answer that. This time we're going to solve a similar problem, but with our same 3 resistors in parallel instead of in series. So we have our 10-volt battery. It's supplying electricity, current, to our 3 resistors in parallel, resistor 1, 2, and 3. So resistor 1 has a resistance of 30 ohms, resistor 2 has a resistance of 70 ohms, and resistor 3 has a resistance of 100 ohms. And we are going to find the total resistance of this circuit, and we're also going to find the total current of the circuit and the current and potential across each one of the resistors. The first thing we're going to do is find the total resistance in this circuit. So the total resistance for resistors in parallel, we have 1 over R total equals 1 over R1 plus 1 over R2 plus 1 over R3. Okay, so that's going to equal 1 over 30 ohms plus 1 over 70 ohms plus 1 over 100 ohms. I don't do a super great job of drawing my omegas here, and they get a little bit sloppy. This tells me that 1 over our total resistance is equal to, I just calculated this, 5.76 times 10 to the minus 2 inverse ohms. Now I have to, in order to get R total, because this is 1 over R total is equal to this, in order to get our R total, the total resistance, we have to take the inverse of both sides. So R total is going to equal 1 divided by 5.76 times 10 to the minus 2 inverse ohms. And this is, similar to what we had to do with our thin lens equations. Then I find that my total resistance in my circuit is 17.4 ohms. So I'm going to write this here, 17.4 ohms. So we see an interesting thing, that whenever we have the same resistors in parallel, for our resistors in parallel, the total resistance is going to be less than those same resistors that you have in series. Since our resistors add up in series, but you've got the inverse relation for our resistors in parallel, your resistance for the same set of resistors in parallel is always going to be less than those same set of resistors in series. Okay. Now that we have found our total resistance in the circuit. We know that our total potential, or the total potential in our circuit supplied by the battery, is 10 volts. Then we can use Ohm's law in order to get the total current. So V total is equal to I total times R total. So I total is equal to V total over R total. So that's going to be 10 volts divided by our 17.4 ohms. So the total current in this circuit is 0.575 amperes. And that was bigger than what we had in our previous problem where our resistors were in series. The current was much less than this. Actually, the current was less than this by almost a factor of 10. So the total current in this circuit is 0.575 amperes. And now we're going to use Ohm's law again and our rules for resistors in parallel in order to figure out what is the current through each one of these resistors and what is the potential across them. Well, we have this special rule for our resistors in parallel. When the resistors are in parallel, the potential across all of them are the same. So we've got 10 volts being supplied to this circuit by my 10 volt battery. So all of these resistors experience a potential of 10 volts across them. Now all we have to do is use Ohm's law for each individual resistor in order to get the current through each resistor. Okay, so Ohm's law, V is equal to IR. So if we solve it for I, like we did right here, the current through resistor 1 is equal to the potential across resistor 1 divided by its resistance. So that will be 10 volts divided by our 30 ohms. So the current through resistor 1 is 0.333 amperes. 0.333 amperes. If we do the same for all the other resistors, the current through resistor 2 is the potential difference across it divided by R2. So that will be 10 volts divided by 70 ohms, and that gives us 0.143 amperes. And then for our third resistor, the current through it will be the potential of 10 volts divided by its resistance of 100 ohms. And the current through it is 0.1 amperes. So I'll put these up in here, 143 amperes and 0.100 amperes. Okay, now what should happen is that for resistors in parallel, the total current should equal the sum of the current through each individual resistor. So if I come over here and I add 0.333 amperes, 0.143 amperes, 0.100 amperes, I should get 0.575 amperes, or actually it'll be off by 0.001. We'll get 0.576 amperes from what I've written up here. But sometimes, you know, you might be off on that third decimal place or that third significant figure, depending on how you round in other parts of the problem. So when we're solving these types of problems, if all that I ask you to do is find the total resistance in the circuit, you can stop right here. Okay. If what I ask you to find is the total current in the circuit, you have to do this step. But if I ask you to find the current or potential across any one of those individual resistors, you might want to think about drawing out a table like this, finding the total resistance, finding the total current, thinking about, are we in parallel or are we in series, to decide, do I have the same current through all of my resistors, or do I have the same potential across all of my resistors? And then you can use Ohm's law to come back through and get either the potential or the current across any of those individual resistors. So that's the process for how we're going to work through some of these Ohm's law problems.